We're going to look at question 3 of the 2023 A-level paper in further statistics. It's quite a long question, broken down into 5 parts, A to E. Let's look at one part at a time. In part A, it says, in a class experiment each day for 170 days, a child is chosen at random and spins a large cardboard coin 5 times, and the number of heads is recorded. So basically, it's a made-up coin being spun 5 times each day for 170 days. Results are summarized in a table, in the first table. And Marcus believes that a binomial distribution with a 0.5% chance of success distribution can be used to model these data, and he calculates the expected frequencies to be in the second table, and we're asked to find the values of R and S. First of all, looking at the first table, we can see that there's more occurrence of 4 than there is 1, for example. There's more 5 than 0 being spun. So it leads me to believe that heads are occurring more often than tails. But let's take a look at the data to see whether that's the case. Marcus thinks that that's not the case. Marcus thinks that it's a 50-50 chance of heads and tails. Part A asks us to find the value of R and the value of S. We don't need the observed data to find the values of R and S because R and S are actually based on the distribution that Marcus assumed. He said essentially Marcus assumed that X follows a binomial distribution of 5 events and 0.5 probability of success. Number of heads, the expected frequency is going to be, now we know the formula for the probability, but to get the expected frequency, we need to multiply the probability by the number of total days. So R is simply equal to 170 days times the probability of X equals 0, which effectively is the same as 170 times the probability of X equals 5 because it's symmetric. Probability of X equals 0 is simply 5 choose 0, which is 1, and then basically there's no success. We're saying is 0.5 to the 5. Using our calculator, we get this value to be 5.3125. So that's our value of R. For our value of S, is going to be 170 times probability of X equals 2, or the probability of X equals 3. It's exactly the same formula. It's 170 choose 2, 0.5 to 0.5 to the 3. You could use your calculator, use the tables. In any case, we get to be 170 times 0.3125, which is the same as 53.125. So this is our value of S. You should also make sure that the total of the expected frequencies sum to 170. In our case, we've got R plus 26.56 plus S, and looks like there are 2 lots of those. 2 times those equals 170. And I'll let you check that's the case. Let's look at part B. It says, carry out a suitable test at the 5% level of significance to determine whether or not the binomial 5.5 distribution is a good model for these data. You should state clearly your hypotheses, the test statistic, and the critical value used. So that's important. We need to write out our hypotheses, statistic, and the critical value. So that's great. Let's write down our hypotheses. That should be fairly simple. H naught is simply that binomial distribution 505 is a suitable model. That's our null hypothesis. Alternative hypothesis will simply be the fact that this binomial distribution of these parameters is not a suitable model. So make sure we answer our question. It's the question is asking us to state the hypotheses. What about the test statistic? So you may remember the formula for the test statistic is in this form. Sum of all of these observed values minus the expected values all squared divided by the expected value. Some of you may remember that this could also be written in this form, which is much simpler for us to work out. And n, the big N, is the total number of observations. Now let's work that out. And by the way, let's write down R equals 5.3125 from our previous part, and S equals 53.125 from the answer to our previous question. So what does this equation come to? The sum of the observed values, we get that in this part, and these are the expected frequencies. Observed value is the square of, so 3 squared over r is 5.3125 plus 10 squared over 26.56 plus 45 squared over s, with s being 53.125 plus 62 squared over s, again 53.125 plus 38 squared over 26.56 plus 12 squared over r, with r being 5.3125. Don't forget to minus 170, the minus n there. Plugging that all into the calculator, we get the value of x squared being 27.4. Let's compare this to the critical value, the chi-squared statistic. And in order to work out the critical value, we need to know what the degrees of freedom is. Here we've got 6 columns, so the number of heads could be 0, 1, 2, 3, 4, and 5. Therefore, 6 columns with unconstrained degrees of freedom would be 6 minus 1 equals 5. Let's take a look at our statistics tables. This is our statistics table showing us the percentage point of the chi-squared distribution. The critical value that I'm interested in has a degree of freedom of 5 degrees of freedom, and I'm interested in a significance level of 5%. So any test statistic that's greater than the critical value has a less than 5% chance of occurring. So 5% chance there, and therefore the critical value that I'm looking at is 11.07. Bring that back to my question. So based on the table, the chi-squared statistic with 5 degrees of freedom and 5% level of significance is 11.070, which is much less than 27.4. Therefore, 27.4 as a test statistic to compare the observed frequency and the expected frequency is way too big when I want the difference of the observed frequency and the expected frequency to be 0. Therefore, there is evidence to reject H naught, that the 0.5 is a suitable model, meaning that it's not a suitable model. So critical value, let's try and answer the question. Critical value is this one, that's this critical value. Test statistic, that's the test statistic, in order to answer the question properly. Now let's take a look at part C. It says NEMA believes that a better model for these data would be a binomial distribution with parameters 5 and p. And it's asking us to find a suitable estimate for p. So find a suitable estimate for the probability of success, for probability of getting ahead. It's quite reassuring because effectively it's hinting that p equals 0.5 is not a suitable estimate, which is what we found in part B. So part C. We know that in binomial distribution, the expected value of x equals NP. X follows a binomial distribution with parameters n and p. And the expected value of x is simply all the x values multiplied by their probabilities. So here n equals 5, n equals 5. And what about each of the probabilities? So each of the probabilities, so for example, x equals, let's say probability of x equals, let's say 0 is simply 3 over 170, because there are 3 occurrences out of the 170 days. Probability x equals 1 equals 10 over 170. Probability of x equals 2 equals 45 over 170, etc., etc. Therefore, we can write this equation. Expectation of x is np, so that's 5p, equals x equals 0 multiplied by 3 over 170 plus 1 multiplied by 10 over 170 plus 2 multiplied by 45 over 170 plus 3 multiplied by 62 over 170 plus 4 multiplied by 38 over 170 plus 5 multiplied by 12 over 170. So evaluating that using a calculator, or let's try that, 10 times 90 plus 3 times 62, that's 186, plus 4 times 38, 4 times 38, that's 152, plus 6 all over 170. And that means 5p is 498 over 170, which means that p is 0.586 to 3 significant figures. This is actually reassuring because it looks like that heads are occurring more often than tails. Therefore, I would be looking for a probability of heads that is slightly above 0.5. That's our part C. So let's look at part D. In the question, it says, to test a model, NEMA uses this value of P. Let's remember the value of P was 0.586 to calculate expected frequencies as follows. Then we are shown a table of the expected frequencies. The test statistic for NEMA's test is 1.62 to 3 significant figures. The question is asking us to state the degrees of freedom and the critical value at the 5% significance level. First of all, let's take a look at a table. It's given us the expected frequency, but we can actually test whether we got the right result in our previous part. And let's call it y. Y follows this binomial distribution with parameters 5 and p being 0.586. Let's work out the expected frequency. So for a number of heads being 0, so probability of x equals 0 times 170 equals 170 times 1 minus 0.586 to the power 5. Let's work out this number to see whether we get 2.07. 1 minus 586 to the power of 5 times 170. Brilliant. So we get 2.07, which is what we get there, here. And we can actually check all the other probabilities or the other expected frequencies to validate that we got the right value of P in our answer to part B. There are a couple of things that we need to remember when we want to work out the degrees of freedom. The first of all is the size of the expected frequency. If the expected frequency, like in this case, is less than 5, we need to be combining that bin or that column to the nearest column. So basically we are combining the number of heads and calling that, let's say, calling that less or equal to 1 head. And then we are combining these two frequencies to make it 2.07 plus 14.65. Therefore, there will be 5 columns to start with. And we need to minus the number of columns by each constraint. First of all, there is a constraint already because we have estimated P. So constraint number 1 is P is estimated. How is P estimated? P is estimated using the observed data from our previous part of this question. The other constraint we have is the total frequency being 170. Therefore, there are two constraints. Therefore, the degree of freedom is 3 because there are two constraints. Okay. Part 2, the critical value. So let's take a look. So we're looking at chi-squared with 3 degrees of freedom, 5% significant level. Let's take a look at the tables. So this is a table showing the chi-squared distribution. We're looking at degree of freedom of 3, and we're interested in the 5% significant level. And therefore, the critical value is 7.815. So that equals 7.815. So that's the answer to part B2. Now let's look at part D. It says, with reference to Marcus's and Nema's test results, comment on the probability of the coin landing on heads and the independence of the spins of the coin. Now let's look at Nema's model. Nema's model was a binomial distribution with parameters 5, 0.586. Marcus's model was binomial distribution of 5, 0.5. And we know that we rejected this model. Let's look at Nema's model. So Nema's model had a test statistic, chi-squared, 3 degrees of freedom of 7.815. So that was the critical value, and the test statistic was given in the question here, 1.62. So test statistic was much lower than the critical value. Therefore, if I were to have hypotheses that, let's say, the H0 binomial 5, 0.586 is not binomial 5, 0.586, then there is not enough evidence to reject H0. So that's Nema's model. So her model is much better. And what can we conclude about the probability of a coin landing on heads? And the probability of coin landing on heads is about 0.586 and not 0.5. So that's part 1. For part 2 is asking us for the independence of the spins of the coin. So what can we say about the independence of the spins and what we know about independence of spins in binomial distributions? First of all, we can say that Nema's binomial model is good. And we can say in binomial models, events are assumed to be independent. So spins are likely to be independent. Because we found a good model that explains the observations, and this model needs to assume the spins to be independent, and therefore we can assume the spins to be independent.